Se il tuo mouse è qui, cioè se no, capito?
Ok. A posto? Ok. Cosa? Vai a sedere subito, vai.
Ah, no.
Okay. We start the last part of section 3, the central engine, and the first speaker is Alessia Tortosa. She will talk about systematic broadband X-ray study of extreme accretion onto supermassive black holes.
Thank you. So, this is a new work which is about the analysis of a small sample of Aegean sources which are created in the super and hyper Eddington regime, actually. So, why super Eddington? Actually, the study of super Eddington accreting sources can help us to understand a lot of topics. As you know, from super Eddington sources, we expect a strong feedback, and also we expect that super Eddington accretion will power winds. Also, it can help our understanding on the growth of the first supermassive black hole at high redshift. And also, in tidal disruption event, we expect that the accretion rate will exceed the Eddington limit. So, which is the difference between super Eddington sources and low moderate accreting sources? The main difference is in the accretion disk, because in super Eddington accretion sources, the accretion disk is expected to be a slim disk, so optically thick and geometrically thick also. And in this kind of accretion disk, phenomena like photon trapping and advection cooling are very important. So the emitted radiation will result to be really really anisotropic, and as I said, we'll expect radiation pressure-driven outflows, and also the X-ray emitting spectra will be pretty steep. So sorry, this is a spoiler. No. You want to be appreciated by the audience. So the sample, these are all narrow line Seyfert-1 galaxies, for which we had priority observation with NuSTAR simultaneously with the XMM and Swift. They are all nearby and unobscured sources which belong to this sample, the Super Eddington accretive massive black hole sample, which include all objects with black hole mass measured via reverberation mapping. And as you can see from this two distribution, why? Wait, please. From this distribution of the black hole mass and of the Eddington ratio, we are going to analyze a region of Eddington ratio, which is pretty extreme and, of course, unexplored. So, before going into the analysis of the sample, I want to focus on this source, which is IRAS 04416 plus 1215, which has very extreme values of accretion rate, and also for its peculiar spectral shape, we call it the dinosaur, as you can see from the plot. So this is the spectrum of the sources compared with the, the median spectrum from the bus sample of Seyfert-1 galaxies. And the peculiarity of this is a typical spectrum of narrow line Seyfert-1 galaxies. As you can see here, there is the drop around the iron edge. The peculiarity of this spectrum, apart from all the absorption feature that we can find in the soft energy band, from the analysis of this feature, actually, we can also constrain two scenarios. You know that it's not very easy to constrain the position, the position of the outflow. So, considering lower and upper limits, you can have different scenarios, but the most important and the most peculiar thing is the coronal temperature, which is very low, and it's the lowest coronal temperature measured so far by NuSTAR. So, about the sample, these are the sources of our sample. All of them show a lot of feature, like absorption feature in the soft energy band, and also pretty strong soft excess. We tested a lot of models to find the best fit model for these sources, and all of them have a pretty steep spectral shape, and the reflection appear to be relativistic reflection for almost all of these sources. We analyzed also the iron emission line from this plot, in which there is the 3 to 10 kV energy range with a simple power law has a fitting model. You can see that the iron line show a broadening feature, and this you can see also this from the analysis of the equivalent width, because these sources show, as you see, the X-ray Baldwin effect, and they follow the prediction from the literature, as you can see here, from the relation from Xu and from Bianchi. In the first, in the top panel, you can see the values of the equivalent width extrapolated from the best fitting model all over the broadband X-ray spectrum. And in the lower panel, actually, there are the values that we extrapolated fitting just with a simple power law model with the narrow Gaussian line. And these values are pretty higher with respect to this one, probably because the narrow core of the iron line, it's enhanced due to the broadening feature from the relativistic reflection. And Speaking about the primary continuum, all of these sources show a pretty high reflection fraction, which is something quite typical. We expect it for neural-lens effect 1 galaxies because they have a reflection dominated spectrum, as for example the well-known case of the source 1H0707, and this is something that it can happen for super Eddington accreting sources because the disk can be clamped and can reflect also the primary continuum, so there is another reflection component. We cannot constrain the high energy cutoff for all these sources, just for 2 of them, and also for the coronal temperature. And the 2 sources for which we can constrain the cutoff are the dinosaur and Markarian 382, which show also a pretty low value of the coronal temperature. And the interesting thing is that if we plot the coronal temperature versus the optical depth, also the super Eddington sources follow the relation that we found in 2018 for sources with low and moderate accretion rate. So it's interesting to look at the position of these sources in the compactness temperature diagram. In this diagram, there is the compactness parameter, which is related to the luminosity and to the dimension of the X-ray corona and the temperature of the X-ray corona. Most of the sources are located in the region in which you can find almost all the Aegean, as you can see here, in which there are the values of the median of the Seyfert 1 galaxies from Rich et al. In 2018. And this is the dinosaur, and this is Markarian 382, which are pretty far away from the region in which all the Aegean are located, in which the pair production and the comptonization cooling are the dominant process in the X-ray corona. So what does it mean? One can say that for these sources, the pair production does not play a significant role, but actually, if we consider a plasma which is hybrid, so composed by both thermal and non-thermal electrons, actually there is the tail of non-thermal electrons that can produce also, can give rise to the pair production and annihilation process. So actually, also in this case, the pair production plays a significant role. And moreover, these sources show also pretty high values of the optical depth, as we expect for super Eddington sources, because radiation pressure outflow can act as a corona with pretty high values of optical depth. So what's next? As I said before, all these sources show warm absorbing feature. Actually, in this work, I just focus on primary continuum and the reflection part of the spectrum, but the next step will be also the analysis of the warm absorbing component, as we did for the dinosaur. Also, the analysis of the variability of these sources is pretty interesting, and we wanted also to extend the sample of super Eddington Aegean, because there are also other sources which have past observation. And moreover, we have another new observation of the dinosaur, which stretched its neck. So something changed, and we wanted also to see what is going on with these sources. So I leave my summary here. Thank you.
Thanks, Alessia. So, questions? No questions? So do you, okay. Yes.
Thank you. They were very, very interesting sources, and I was just wondering. So you see now preliminary the increase in the X-ray flux, right? In this object that was a dinosaur. Was this that you showed last? Yes. Yeah. Oh, so this the new stuff is the blue stuff, the blue spectrum. Do you plan to also have the optical follow up to see what's happening?
Yeah, we are going to see also in the optical band what's going on.
It would be very interesting to see if there's some reaction to this with in the optical spectrum. Yeah. So thank you very much. Very interesting.
More questions? I have one. So are you planning to check long-term variability as well? Also, to check.
That's an option also.
Okay.
Yes, we are planning to observe also, to check a lot of things, also the optical and the long variability. Yeah.
Okay, so thanks, Alessia. We move to the next speaker, Marcello Giroletti. Okay. Yes. Okay, now Marcello will talk about a multi-instrument view of the black hole and the relativistic jet in M87.
Okay, thank you, Francesca. So, thanks to the organizers for allowing me to talk here, and to you all for being here. It's a really big emotion. I'm going to complement what Bettina said earlier about the EHT observation of M87, giving a multi-instrument view. And this is work that I've been doing with a lot of collaborators, but in particular I would like to highlight the names of Giacomo Principe, Evgenia Frakachenko, and Hugo Ro and Yazukui, who collaborate with me for various aspects of this research. Since there's not much time, I will skip the first slide, but the bottom line there was that I will try to show you three main aspects of this multi-instrument view. The first one is the campaign that was organized in 2017 around the observations with EHT. So you see a few keywords here. This global is the first keyword because it really was an effort that involved institutions all over the world. Radio to very high energy, really we went across the entire electromagnetic spectrum. 2017 is again what we are going to compare our data with. M87 is the target, and EHT, of course, is the reason why all this was done and then presented in this paper. So I promised the multi-instrument view, and here you get the multi-instrument view. The radio data are here: ALMA, EVN, EAVN, VLBA, GMVA, and of course the famous EHT donut. UV and optical here, SWIFT and HST, you appreciate the large-scale jet. And then high energy with Chandra, which is the only instrument that is able to resolve M87 at high energy. And then NuSTAR, the very high energy Cherenkov telescopes, and Fermi-LAT. And each of these instruments, of course, had a lot of details that I'm not going to describe, but really the analysis was very careful, very interesting, and the results are summarized here. So you see we observed for about 60 days. You see Fermi with this continuous coverage here, and then every other instrument with their snapshots. The 4 ticks here represents the 4 sessions of the EHT that resulted in the famous image. And this is the span in observing frequency, energy, and this is the other way around. So in the x-axis you have the energy, and in y-axis you have the SED. So this is the simultaneous SED of M87 around the time of observations from EHT, going from a few gigahertz up all the way to very high energy emission. Of course, there is a lot of work that can be done with this data. These data are actually public and available, so everybody is encouraged to go and test their model. I'm just going to present very quickly 2 of the modelings that we carried out, and they are shown as models 1AB and 2. So in yellow, the 1A, which is basically trying to fit the innermost part, so trying to fit the EHT data. You see it goes through the EHT measurements. They're both leptonic models. So this first model is successful in reproducing this part and going through the optical and the X-rays, but completely fails to reproduce the high energy and very high energy emission. While on the other hand, model 2 does a much better job in dealing with this part, but then it falls way below all the low energy data. And this is one main thing that is not surprising, because people don't always make an effort to fit the radio part, but keep in mind that in this case is actually the radio emission is actually millimeter emission from the most compact region. So in principle, one would like to really go and catch that point. So the idea is that there is not a single zone model that is able to reproduce the entire SED, but actually one needs to consider at least more than one emission region, and perhaps even a more complex picture. And so to summarize this part of the work, I think the first message is that structured jet is necessary, and by structured, one can think of really any kind of model. I'm showing here just the limb brightening total intensity image that we produced with Kazuhiro Hada back a few years ago. So I don't mean that necessarily we need to have a stratified jet in the sense of a transverse structure, but this is clearly something that we find in the images, and is also something that has been invoked several times to explain, for example, the production of neutrinos. And this again ties to Christina's talk this morning, because the other point that we find is that there is probably a transition from a magnetically dominated part at the very base of the jet to a more particle-dominated farther downstream. So none of these is a final statement, of course, but there are hints and occurrences that recur in these jets. So this is the first result, I think, that is worth carrying home. But again, we have mentioned magnetic field, magnetic energy density, and so perhaps it's time to move on to the second part, where we're talking about the polarization of M87. It's interesting, M87 is very strongly polarized on large scales, so on several kiloparsec scales. The magnetic field is very well described by polarized emission in radio and also at higher energies. But when we go near the core, the source is basically depolarized, and in fact until a few years ago there was no evidence of any polarized emission in M87 until this paper, again by Kazuhiro Hada and collaborators at 3 millimeters, that revealed a hint of polarized emission. So what is the second point in my talk is the results of this campaign that we carried out with the VLBA at 7 millimeter at 1.3 centimeters, so about 10 times lower in frequency compared to EHT, and so 10 times farther downstream in terms of angular resolution. But the important thing is that actually we did get a detection for polarized emission in this source, and not only we got a detection, but we got a resolved structure. You see this is a double, and the other interesting part is that the double is symmetric with respect to the center, so it's also convincing that this is not instrumental, because basically if it were instrumental it would be proportional to the total intensity, and this is clearly is not. You also see the trend here. Perhaps you cannot read the axis that. Don't worry. Basically, the idea is that the electric vector polarization angle goes around the core, and this is suggestive of an helical magnetic field that threads the base of the jet. The other very interesting thing is that we went back to previous data and found that this structure was already there in data that were taken about 11 years ago, and basically they require just a more careful analysis to demonstrate this structure in a convincing way. Since we observed with 2 frequencies, we could try to have at least a glance at the dependence of the polarization angle as a function of frequency, and that's what can give us information about the so-called Faraday rotation, so how the polarization angle changes because of the presence of an ionized medium between the source and the observer. And what we get is this value of the rotation measure, that is a few times 10 to the 4 radians per square meter, which is a value that can be compared, as I mentioned earlier. The source, M87 jet, is detected in polarization farther downstreams, so we could compare this result with what happens farther downstreams, and also thanks to the ALMA data that appeared just after, for the inner part, or at least for the highest frequency, the higher frequency, we could really try and compare this value with what was suggested by other wavelengths. And the thing is that this value is not particularly high as one would expect in the very inner part. So this is suggestive that perhaps something is to be better understood in terms of the density of the accretion flow in the innermost part. What we can say for sure is that we do not observe reversals of the rotation measure, and that means that it's most likely that the screen is external and not due to the magnetic field of the jet itself. The last point, as I think time is running, is again a way to connect the various scales in this jet, because as I mentioned earlier, these for example, these polarization results, we are just looking at a window that is in between the EHT scales and what was known with the VLA, for example, or even EHT in farther downstreams. So it's really important that we try to connect and match all these regions, and even the SCD clearly suggests that the total emission is the combination of several regions. And so what we can do is to actually go and monitor the source regularly and try to compare the small scales, again with the VLBI technique, to the large scale. For example, you saw from the set of images at the beginning that M87 has a rather straight jet extending for several kiloparsecs, but here there is a result that we published in 2012 where for the HST1 knot, that is about 70 parsec downstreams, there is a clear rotation as time goes by, so this is about a decade, and the structure clearly changes its position angle. And so this seems to suggest that the emission does not always move, where the features do not move ballistically along straight lines. And what we are doing, thanks to the collaboration with the East Asian partner, is to monitor regularly M87 with about a monthly cadence in what we call the Eating VLBI project. And clearly with the 3 countries, Italy, Korea, and Japan, we have a total potentially of 10 stations. They do not always observe together, but we do get enough to get good quality images, not as spectacular as with the full VLBA, but good enough to have a statement, a quantitative assessment of the position angle. And this is, again, the work that our East Asian collaborators are doing, and clearly we see that the inner jet is changing its position. You see here a bunch of epochs from the early 2010s to almost 2020, and there is clearly a wiggling of the jet with a hint of periodicity. Of course, this is not many periods yet, but it is clearly a trend here. So going back also to what we discussed this morning, for example, the need to look at light curves or periodicities to understand if there are binary black holes. Well, we know that M87 does not have a binary black hole, but something in its jet mimics this behavior. So watch out when you look for signatures, because clearly jets are subject to instabilities that can produce this kind of trends. And I think that's it. Just remember that there is a full SCD available for M87 with an attempt to fit, but again, the data are there and you can feel free to add whatever you want. And there is more work going on to tie all this scale together. Thank you.
Thanks, Marcello. Unfortunately, I can take only one question because we're running late and we have to leave the room at 7. So, is there one question for Marcello? Yes, Francesco. No, you need the microphone.
Very quickly, the degree of polarization when you look outside. Inside is 2-3%. Outside, can you just remind me? 10%. Okay, thanks.
Okay, so we can, so while switching to the other presentation, I have a quick question. So do you have any sign of this wiggling at larger scales? You should see something, right?
Not really, because the jet is actually, I can go back to the image, but it's actually quite straight. So
Yeah.
The innermost part where you can see this is HST1. Is HST1, but HST1 is still relatively near because it's 70 parsecs. Thank you.
And thanks, Marcello. Okay. Then we move to the next speaker, Francesco Rossini. Will talk about constraining Aegean coronae with spectropolarimetry.
Okay. So yeah, good afternoon, everyone. In this talk, I will focus on the perspectives for constraining the geometry of hot coronae in non-jetted Aegean thanks to X-ray spectropolarimetry, which is finally enabled thanks to XIV, the NASA joint mission that is flying since December 2021 and already started providing very interesting results on different types of objects. Concerning our problem, so the hot corona is the region of Aegean, which is responsible for the X-ray emission through comptonization of the optical UV photons from the disk. Essentially, this process produces a power law spectrum with a cutoff that is often observed at high energies, depending on the coronal temperature. So from the spectral parameters, we can constrain the physical parameters of the corona, so the temperature and the optical depth. However, nothing is actually really known about the geometry, if not that the corona is located in the inner part of the accretion flow. But the shape is completely unknown. For example, the corona could be a slab covering the accretion disk, in which case it could result from instabilities occurring in the disk. It could be a spherical blob. Or if the corona is the base of a jet, or possibly failed jet, it could rather have a conical shape. So the shape is related to the physical origin of the hot corona. Now, spectroscopy is not able to distinguish between the different geometries, but polarimetry is. Indeed, the polarization signal measures deviation from the spherical symmetry. So, as I said, XP finally enables these kind of polarimetric measurements. Its bandpass is 2 to 8 kV, so where the primary emission from the corona dominates. And for bright Aegean, the typical minimum detectable polarization degree is going to be the order of 2% with an exposure of 500 kilosecond, meaning that this is the minimum polarization at 99% confidence. So, in order to make sense of the upcoming polarimetric measurement with XP, we run simulations on the expected polarimetric signal in radio quiet and unabsorbed Aegean using a Monte Carlo comptonization code called MONC that is fully relativistic and calculate the comptonized spectra in Kerr spacetime. And setting physical parameters consistent with MCG 52316, which is indeed the first Seifert galaxy that XP will observe. Actually has already observed, but it was already, it was exactly in these days. So concerning the signal, so the polarization degree and angle is clearly quite different for the different geometries that we can assume. So the slab case clearly produces the largest polarization degree, while the spherical case, the lowest polarization degree, and the conical, which is somehow in between, so an intermediate level. I forgot to say that the cone here is also in outflow and with the velocity of 0.3 c, meaning that it does not reach the escape velocity. Since we are dealing with a radio quiet source, this is not able to produce a powerful jet, but rather it's more consistent with a failed jet. Also, the polarization angle is quite different between the different cases, in particular between the slab and the spherical and conical case, there is a difference of 90 degrees. Now, the signal depends on the inclination of the source. However, in the case of MCG 52316, this is an intermediate inclination source, so it is a very promising object to carry out this kind of measurement. I don't know. I think I blocked something. Okay, yeah. So indeed, similar result if we focus on a specific inclination and we look at the spectrum of the polarization signal. So the degree and angle as a function of the energy. Clearly, there is a significant difference in terms of polarization degree and angle for the different geometries. However, the spectral information is quite crucial because different spectral shape imply different polarization degree. For example, here is the case in the case of the slab for different values of the photon index and temperature. So, like in the two spectra here in the right panel, the polarization degree is quite different. So, and the same. Oops, sorry. Yeah, I mean the same is for the spherical geometry. So it is important to complement the polarimetric observation with the spectral information. Indeed, for example, in the case of MCG5, we are going to have a new star observation simultaneous with the XP1. Okay, I think I can conclude and thank you.
Thanks, Francesco. One question. No questions? Okay.
Could you remind us how many Aegean will be able to be targeted by XPA, roughly? I mean,
well, in the first-year plan, there are two ciphers, two unobscured ciphered ones, which are MCG5 and IC4329A, and then there will be the Circinus. Yeah, and for the first year, that's it.
3, okay.
Yeah.
Thanks.
Okay, let's thank Francesco for his talk. We move to the next talk by Roberto Serafinelli, Observing the Coldest Hot Coronae of Aegean with New Star.
Thank you. So, it's very nice to be here. Thank you for having me, finally in person. So, I'm going to talk to you about the new star spectra of sources with particularly cold coronae. So the X-ray spectrum of Aegean has a very, as we have seen in a few talks today, has a typical spectrum. There's a power spectrum, where the number of counts goes as the energy to minus gamma, where gamma is the photon index. This power law breaks at a certain energy called the cutoff energy, which is tied to the coronal temperature by this relation. The cutoff energy is 2 or 3 times the coronal temperature, depending on geometry. The temperature ranges from a few keV to a few hundred keVs. And so far, they mostly have samples where higher temperatures have been studied. We're going to focus on the lower end of this distribution. To do this, we have selected the sample. We started from the BAT catalog that lists a lot of X-ray properties of Aegean. We selected those ones that have cutoff energy less than 150 keV. We only selected those that have upper and lower bounds, so no upper limits, no lower limits. Of course, they must have public new-star data and a sufficient number of counts. Then we made quick spectral fits to see if we can find upper and lower bounds for the temperature also for the new-star spectrum. And we end up with this small sample of 13 sources. This is our, our strategy. We fit all observation together. This is done by assuming that temperature, optical depth, and other properties of the continuum, with the exception of the normalizations. The normalization does not change from observation to observation. We have checked that this is true. This assumption is justified, and we make the first fit to try to constrain the reflection for the sources. And then we fix the reflection, and we let we add a continuum component, a comptonization model that allows to study both slab and sphere geometries for the corona that you have just heard about from Francesco's talk. So we plot here the temperature as a function, the contrary, the optical depth as a function of the temperature. And we found that in both geometry, these two quantities are much correlated. And we find that the slope of this distribution is consistent with the ones found for samples of higher temperature. Also, for those sources that have a measurement of the mass, from example given reverberation mapping, we try to see if there is any dependence or correlation of the temperature from the mass. We do not find any, as in past studies on higher temperature sources, and same goes for the Eddington ratio dependence. There is none. So apparently there are no from the spectroscopic point of view, there are no differences between low temperature and high temperature sources. But what about variability? So we're going to use these two tools, the axis variance that measure the variability of an observable compared to the photometric error of the measurement, in this case the count rate, and also the fractional variability amplitude, which is the square root. We're going to use these two parameters indifferently. The problem with these two quantities is that they depend on the length of the light curve. So this is a sum. So the more points you have, the more the axis variance is large. So we need to normalize for source to source. This is the typical shape of a power spectral density of an Aegean. It has a trend as f2 minus alpha up to a frequency called a frequency break, and then it has another trend leftwards of the frequency break. We assume that we are in this region over here, in the region where the f2 minus alpha trend is when the trend is f2 minus alpha, and we assume an alpha that is 1.2, which comes from an ensemble result on quasars. Under these assumptions, the axis variance scales as this with this law over here. So we scale the axis variance to 10 times the light travel time, so 10 Rg over c. And we find a dependence on the mass, a very good correlation on the mass, with low probability of finding this correlation by chance. This is a result that was already known in the softer X-ray band, the 210 keV band. But we also find that the variability has some anti-correlation, minus 0.6, with the temperature of the source. And while one may argue that this trend is driven by these two sources over here, this is what happens when we add more sources. We add some sources with higher temperatures from the Rani et al. Sample, where FVAR are computed by that group, and also we computed FVAR for some higher temperature sources from the Tortosa 2018 sample, and we computed the FVAR. So we find that the sources lie on the same line, and if we fit these points as well, the correlation becomes much stronger. The slope is almost the same, and we have a much lower probability of finding this correlation by chance. Well, we made also some simulations of EXTP, which is a telescope that is probably is probably flying after 2027. It has four instruments: a spectroscopic focusing array, which is a telescope on the soft X-ray band from 0.5 to 10, a large area detector for higher energy, for the higher energy band. It goes up to 30 keV. It also has, remarkably, a polarimeter in the 210 keV energy band, and a wide field monitor. So since it arrives up to 30 keV, this instrument is ideal for studying low temperature sources, but also it has polarimetry information. We made some simulations. These are 100 kiloseconds on 4C 50.52. So the contour plots of optical depth and temperature are much thinner because it has a higher. We have much more statistics with these instruments, but this telescope also allows, as I said, simultaneous polarimetry information. These are simulations made with Monk, like the ones just shown by Francesco, where we see the polarization degree for as a function of the inclination for a slab corona, conical corona, and spherical corona, with 500 kiloseconds of PFA. We find a minimum detectable polarization at 99% confidence level of about 1.65%, which is this red line here. So with this exposure, we would be able to constrain the geometry of the corona for a wide range of possible inclination angles. So in summary, we have analyzed a sample of 13 Aegean with low temperature. We find that spectroscopically they don't show much difference with their higher temperature counterparts. In particular, they have the same relation between temperature and optical depth. They do not show correlation with mass or Eddington ratio, but they seem to be more variable. And then we've shown some simulation of EXTP showing that with simultaneous spectroscopy and polarimetry, we should be able to distinguish different coronal geometry. Also, I would like to add that the wide field monitor will be able to let us study longer timescale variability as well. Thank you.
Thanks, Roberto. Questions? Yes, Alfredo.
Hi, I hope these are not too many ignorance-driven questions.
Can't hear you.
Si sente?
Both.
So, no, a couple of questions. Regarding the anti-correlation of variability, the two anti-correlation you reported.
For the temperature. With the temperature.
Yeah. No, there was also also the other one with mass.
With the mass.
Yeah.
Yeah, this is a well-known correlation.
Exactly.
Yeah.
No, it was just a curiosity. What if you renormalize the times of each observation with the black hole mass?
This is something we have sort of done. So we normalize to the light travel time, which depends on RG, which is a function of the mass. We could also do that with the break time. Also, we haven't yet done that, but it's also another idea.
Okay. And if you do this, the relation is still there, or it disappears?
We have done it with this.
Okay. Sorry, I missed it. Okay.
There are more urgent. Yeah, one from Maurizio. Quick one.
The slope that you assume 1.2 was the slope of the steep part of the power spectrum?
It's a result of the ensemble quasar. So yeah, it is done assuming that we are on this side, because quasars are much more massive and more luminous than Seyfert galaxies. So a frequency break on quasars still has yet to be found, because the time scale is much longer and we do not have enough information yet.
Thanks.
We do not have measurements for such a long time yet.
Okay, thanks, Roberto. We now move to next speaker is Eleonora Puzzoni. She will talk about the role of the magnetic recognition on particle acceleration in relativistic jets.
Thank you. Good evening, everybody. I'm Eleonora Puzzoni, a PhD student from the University of Turin, under the supervision of Andrea Mignone. First of all, I would like to thank the organizer for giving me the opportunity to give my first talk in person. So for me, it's a big emotion. And today I will talk about my research, which concerns particle acceleration in relativistic jets. The study of particle acceleration in high-energy astrophysical sources capable of releasing electromagnetic radiation, powerful electromagnetic radiation, such as supernova remnants, gamma-ray bursts, pulsar wind nebulae, and of course jets from Aegean, is important for the interpretation of the observed spectra from these astrophysical sources, because that would mean to understand when, where, and especially how particle accelerates, because the real challenge is to model the higher energy part of the spectrum. Magnetic reconnection is thought to be responsible for the thermal emission from this flow. But how does it work? First of all, the plasma must be resistive. This means that the physical resistivity that we call the eta must be different from zero. In this way, magnetic field lines of opposite polarities rapidly annihilate, and magnetic energy is converted into kinetic and thermal energy of the plasma, becoming at the same time available in creating a non-thermal population of accelerated particles. This process can occur as a time-dependent and unstable process triggered by the Tiering mode instability. In this case, an initially neutral current sheet tends to fragment into a number of fixed points that are the blue points, that are the magnetic field null points, in which the electric field is very, very strong. and in O points, often called plasmoids, that are regions of high current density. So we solved the bidimensional resistive relativistic magnetohydrodynamic equations for the fluid here on the left, while on the right we have the physical relevant quantities. But the part that most interests us is that the particles, that are the blue part, evolve on the fluid on the background. In fact, the particles, this set of equations are coupled by the fact that the particles follow the electromagnetic field of the fluid. We consider a very large number of particles, so it is impossible to solve by hand all the equations for the particles at any instant of time, and concurrently those for the fluid also in any point of the domain. So we need numerical simulations. Oops. Okay. For this reason, those equations are implemented in the Pluto code that was created by Andrea Mignone, and we consider test particles. This means that the particles are affected by the electromagnetic field of the fluid, but do not exert any force on it. So these are the initial conditions. The initial configuration considers a bidimensional domain of size L and half L. The magnetic field follows a hairy sheet profile, where A denotes the initial width of the current sheet along the y direction. The plot on the left shows the initial condition for the pressure, and in all our simulation we have set sigma, that is the magnetization parameters, equals to 10. For convenience, the physical resistivity is prescribed from S bar, that is the Lundquist number corresponding to the current sheet initial width A, where VA is the alpha velocity. Test particles are evenly assigned to grid zone with 1 particle per cell, and their initial velocities follow a Maxwellian distribution. So we first consider the evolution of the tearing unstable current sheet of the fluid in the background. So in this video we will see on the top the evolution of the pressure of the fluid, while on the bottom we will see the growth of the perturbation over time, marked by this point. We will see 4 main phases marked by 4 different colors. So at the beginning, the current sheet started to shrink at the edges of the computational domain, entering its first linear phase. Then the process continues as the current sheet becomes thinner and thinner, entering its second linear phase. Then the current sheet fragments into a number of plasmoids that begin to merge, and at the end, the system reaches a saturation phase in which all the plasmoids merged into a single large island. We then consider the dependence on the growth of the perturbation on the grid resolution, marked by the colors, and on the physical resistivity that is marked by the 3 different panels. We clearly see, if we look at the purple and the orange curve, that as the Lundquist number increases, the convergence is achieved at higher and higher grid resolutions. Moreover, if the Lundquist number is increased, the physical resistivity is decreased. So it risks being confused with numerical diffusion, over which we have no control rather than increasing, in fact, the resolution. I want to underline that even in 2D we are struggling, because to resolve the current sheet we need at the higher resolutions 40 up to 80 points on the current sheets. And just to give you an idea, the last simulation took us about 2 weeks. So for now, unless more advanced techniques are used, it is impossible to switch to 3D if we want to reach convergence. Then we focus on the dynamics and energetics of test particles that evolve concurrently with the fluid. In this video, we can see the most energetic particle position over time superimposed on the plasma pressure in grayscale, and the particles changes color according to its kinetic energy. we will see that the particle first accelerates at an X point, then due to the repeated island merging, and finally due to the first order Fermi mechanism, this is trapped inside the final plasmoid that is contracting. Then we consider all the particles, so we divided them into beams of energy, and this video will show the temporal evolution of the spectra that so changes color as time grows. We see that at the beginning, the particles follow a Maxwellian distribution, as we expected, but as time grows, a power law followed by a high energy cutoff appear, and the index of the power law at the end of the computational time is equals to 1.2. Oops. We focus again on the dependence on the grid resolution and on the physical resistivity of the particle spectra at the end of the computational time. We see that in the lower Lundquist number case, a double power law is formed, but if we increase the Lundquist number, only one power law is present with the same spectral index. I want to underline the fact that this is an extension of a previous published work in which we consider only the classical magnetohydrodynamic case. On the bottom we see the spectra in the classical magnetohydrodynamic case, while on the top we see again the spectra in the relativistic case. We see that the spectral behavior is quite similar, because if we increase the Lundquist number, so if we go on the right, we see that the power law index remains substantially the same. No. Okay, it's clear that if we want to reach convergence, a balance between physical resistivity and the grid resolution must be achieved. But we've proven that relativistic magnetic reconnection is a viable candidate for producing population of non-thermal accelerated particles that emit the spectra in astrophysical non-thermal sources like active galactic nuclei. So for comparison, here you can find the computational time, the length of the domain, and the maximum kinetic energy achieved by respectively the protons, the electrons, and protons, because our code is applicable to protons in electron-proton plasma, but also to electron-positron pair plasma. So we can compare them with the observational results that I found, because my data come from only numerical simulation. I have to say that this comparison is only qualitative, because a more accurate comparison should require a model with radiative losses. So our model for now does not consider radiative losses. So for now, it is only a qualitative comparison. But we are looking forward to insert this on our model in the future, and we would like also to change the boundary condition, because for now are periodic and this is a limit, and we want to try to move to 3D with more advanced techniques. Thank you for your attention.
Thanks, Eleonora. Yes, 2 questions, quick, please.
Hi, very nice talk. I have a question about the end of part 2, the video of the function after the particle. Yes, in that one. When you play it, there are 2 moments where the function jumps and there is a discontinuity, and I was wondering if you know what that is for. So from the first one to the second group, and then...
Oh, okay. Only by the fact that I consider only certain data, because there were a lot of data, so I consider the first part, the intermediate part, and then the last part. You're welcome.
Thank you. I wanted to ask if you consider in your simulation also different value of sigma and beta varying this value and different initial value of sigma and beta.
Okay.
And if the power law and the cutoff were in agreement with the particle in a cell simulation with similar initial values.
Okay, no, for now, we didn't change sigma, but we are looking forward to change sigma, put it equals to 50 and see if there are some changes, and also to beta, because we want to, in fact, compare our result with, for example, particle in cell simulations that use a very small beta. And so in the future, we will do it.
Okay, thank you.
Okay, let's thank Eleonora. We move to the last talk of the day by Gabriele Mazzeu. Supermassive black hole wins in X-rays.
Thank you very much. I will be really quick. So I know it's the last talk of the day. I don't want to be annoying. It's more than I usually am. Okay, so yeah. This thing. Okay, so left and right? Okay. All right, so thank you very much to let me introduce this work I've been doing for a while. I'm part of the Subways collaboration, which is an international basically gathering of scientists that are basically focused on ultra-fast outflows, okay? And essentially this is a characterization of supermassive black holes in Aegean. So what are they? Okay, so we know that nearby the black hole in this region we have extreme like a radiation pressure or magnetically things happening. But essentially what happened is a lot of matter gets really pushed out in form of ultra-fast wind. So the way in terms of spectroscopy is concerned, which is the pointer. So yeah, so what happens is that in terms of X-ray spectroscopy, the way basically the imprint of this ultra-fast wind are seen in the spectra as an absorption feature, obviously, and the degree of they're basically blue shifted, and this degree of blue shift can tell us obviously how fast are basically flowing. But also what we found really importantly is that the emission feature is also essential. It plays a key part in understanding, well, the geometry of the wind, but then also the kinetic power. And for this reason, because they're really fast, they're covering a large fraction of the sky, they are prime candidates for feedback. Anyway, so actually, I just want to say that this is PDS 456, but this is also one of our GEMO subways, and we can see also the P-Cygni profile. But anyway, that's for another talk. So this project was assembled by Marcella Brusa, and essentially, well, what was basically the selection criteria was that at least some of the sources need to have at least a snapshot. But then what we really wanted, we really wanted to do was to basically cover a redshift range between 0.1 and 0.4, which I'm going to tell you a little bit later why this is so important. And basically, essentially, we wanted to have also a decent amount of counts because we want to have a comprehensive, basically, spectroscopy. So in total, okay, we have 17 sources that have been observed in the AO18, and then 5 sources were already like in the archive, obviously like prior to that, and so total of 22. Okay, so. First of all, with all this work I'm going to do, please go and check out Victoria's her poster, which is outside, she's taken it to another level. She take the whole subways to a different way. But all I want to say is this: essentially, basically the selection in terms of redshift is really important, because all this work that's been done in the past by, for example, Tombesi, Gofford, is basically low Z select a sample, and then we have the high redshift sources by charters. So what we wanted to do essentially was basically bridging. It was basically doing well. We wanted to bridge this gap. Okay, so we wanted to see what we would call the intermediate, like a redshift. So. The thing I found straight away, although the ion K is between, let's say, 5 and 10 keV, I wanted to, anyway, to parameterize the level of the continuum. So the first thing that I found is that you can see here the subways in green. So basically, the distribution of our photo index is basically what we would consider a normal. Well, it is within the normal Seifert kind of thing. So it's around 1.8. So if you compare them to the other big work that has been done, but also, okay, what is really important is like, yes, I did want to basically parameterize the whole continuum from 0.3 to 10. And the first thing I did is I wanted to do a non-physical, just like a parameterization, essentially, a phenomenological model. So we took, for example, and most of the sources have like a soft excess, which we had the two component, like a black body component. But I don't want to get into the details of the physical meaning. However, I couldn't help myself to basically just to check if we have some like a warm absorption, and basically I found 60-65% of the sources do have a warm absorption, and also what I noticed is that all the sources that then I'll tell you later that we found with ultra fast outflow or some kind of or some absorption feature, they also have like a warm absorber. So anyway, I just put it out there, right? So, okay, so what we did then, we basically parameterized the continuum, and then what we did was first did like a blind search. Okay, we got this like unresolved kind of Gaussian, and we go through 5 to 10 keV, and by going through, we see here, for example, these two sources, which are incredible, because you can see here the really strong absorption feature, but also in this one in particular, the GEMO subways, what we can see here, we can see the P signal-like profile, which is a big absorption and a broad emission. So this is going to be a paper on its own anyway, but essentially, these are all the other sources. So these are all the results we have with a blind line search. Okay, so, but then what we did to have a bit of a quantitative analysis, we ran a Monte Carlo simulation, and we found essentially, I need to hurry up because I've got a train to catch too. So that, we got, essentially 7 of the sources have a significant, we found absorption feature with a significant greater than 95%, but 2, the first 2 I show you, have a great significance, okay? So, which is about 30% of the sample, okay? So, the other thing I noticed is that, again, I'm just putting it out there, but what I see that somehow these are all the mean values of the different work done in the literature. But what I can see that the mean distribution or the mean like velocity of the outflows essentially increase with Z essentially, because the charters are high Z and so on. So maybe this is just a trend. I'm not saying anything, but here to put more into context of what has been happening. I mean, you got to appreciate what the subway sample tried to do here. We tried to basically fill in this space that was empty, completely empty. So So we put together all the Tom Basey and Goff and charters, and we do see a positive correlation between the bolometric luminosity and the velocity of the detected ultrafast outflow. And basically the slope is very consistent with the slope I found a few years ago, with obviously on a smaller scale with just one source, PDS 456, but because it was so well studied, we had a lot of observations, and we found essentially a similar slope. What this is telling us, maybe, this is an indication that ultrafast outflow are probably are radiatively driven, or the dominant, basically, mechanism is basically radiatively driven. Okay, so in summary, I want to say, okay, we define the 30% of the sample, we have a significant detection of absorption feature that can be associated with ultrafast outflow. We will do in the future a more physical modeling of these features, so we can have a proper identification and physical properties. Anyway, thank you very much.
Okay. Questions for Gabriele?
We need to go home.
What time is the train? Okay.
No, don't worry. No, I said we need to go.
No questions? I have one. So, did you expect this fraction, considering the locus of the region that the subway sample is occupying in the L-ball plot?
To be honest, I didn't quite think at that point. I mean, it was just basically not a coincidence, but yeah. Well, we do know that, for example, ultrafast outflow can be ubiquitous. So I think that this number, I was expecting a similar number. Okay, 30, 40%, but yeah. Anyway, we need to populate this kind of thing with more.
Okay, then let's thank Gabriele. Let's thank all the speakers of the session and of the day, and we can go home, and we see you tomorrow again.